Hello, everyone. In today's lesson, we will learn about the automatic detection of CNC lathe parts. CNC lathe parts are one of the most common types of parts, with the main surface being external cylindrical, such as plane shafts, half shafts, stepped shafts, spline shafts, camshafts, and so on. These parts are widely used in transportation, construction, chemical, and other industries. Due to their special shape, V-blocks and other positioning elements are often needed during clamping. The main contents of this lesson are divided into 4 parts. 1. Inspection analysis. 2. Clamp workpiece. 3. Calibration of star probes. In this lesson, we need to understand the positioning and clamping methods for CNC lathe parts and master the calibration methods for star probes. Let's now dive into the detailed learning. Step 1. Analyze the part. Familiarize ourselves with the inspection content and compile a list of the required measurement dimensions. By analyzing the drawing, we can see that reference points A, B, C, and D are clearly defined. Based on the principle of reference overlap, when establishing the coordinate system, priority should be given to using these reference points for alignment. After carefully analyzing the drawing, we organize the 10 measurement dimensions, associated features, nominal values, and tolerances into a table, as shown below. Step 2. Clamp workpiece. Since the part has features to be measured on both ends of the internal holes, it should be placed horizontally, with its rotating axis parallel to the y-axis of the measuring machine. Additionally, it is important to raise the part slightly during clamping, so that when the part is rotated to the horizontal position, the measurement stroke in the negative Z direction is effectively ensured. The most commonly used fixture combination for rotary parts is the V-frame or V-block clamping solution, which is also employed in this case. To ensure stability of the V-block clamping, the fixture adopts a 2-end support method. Since the diameters of the external cylindrical surfaces of CNC lathe parts are often different across multiple sections, we have designed one V-block fixed at one end and the other V-block adjustable in height at the other end. After placing the part, the height on one side is adjusted until the part is securely held without any wobbling, relying on its own weight to maintain a stable clamping state, as shown in the diagram. Step 3. Calibration of star probes. First, configuration of star probes. For measuring the width of internal groove and the diameter of the inner cylinder of a part, the star probe is the optimal measurement solution. 1. The star probe is easy to configure and offers unmatched advantages for measuring internal groove-like features, which other types of probes cannot achieve. 2. For measuring external grooves on the part, there is greater freedom in probe selection. The star probe can be chosen, or a vertical single probe can be used instead. 3. For measuring the width of internal groove and the diameter of the inner cylinder of a part, the star probe is the optimal measurement solution. While a disc probe can also meet the requirements, special attention must be paid to selecting the correct size of the disc probe. Therefore, based on the feature distribution of the part and the required measurement range, the star probe is selected for measurement in this case. The probe selection is shown in the diagram. The installation of the star probe is shown in the diagram. The probe's threaded connection is passed through the central hole of the star probe, with the probe's thread connecting to the probe head. Before rotation, ensure that the star probe is roughly parallel to the machine's axis in the horizontal direction to avoid probe interference during measurement. Next, let's look at the actual operation. Calibration of probes. Let's first take a look at how to configure the star probe. Open the probe toolbox and define the probe file name in the probe file section. In the drop-down list, sequentially select the TISA TMA adapter and the TISA star P probe. Here, a 10 mm extension rod is required. Next, select the 2BY20 star probe. It is important to note that the suffix for the new probe type is star TISA. Once the first probe is selected, 4 empty connection slots will appear below. These 4 slots define the 2nd to 5th probes of the star probe. Here, we will choose 2x30 probes, with the suffix TISA. Note that in the TISA star 2BY30, the 30 refers to the distance between the ruby ball connection line of the 2 probe rods, i.e., the distance between the 2nd and 4th probes. This completes the definition of the star probe, which will now appear in the probe list from T1A0B0 to T5A0B0 for the 5 angles. Click Add Angle to add the angles A90B0 and A90B0, and click OK. We will see that each time a new angle is added, 5 new probe angles will automatically appear in the probe list. If the newly added angles are not used in the program, for example, if T5A90B0 is not needed, simply select it and click Delete. Next, place the standard ball support rod vertically upwards and fix it at the center of the workbench. Click Measure, select all A0B0 angles, and then select TA0B0. Hold the Ctrl key and sequentially select T2A0B0, T3, T4, and T5A0B0. Adjust the appropriate measurement parameters. It is important to note the vector direction of the standard ball. Since the standard ball is positioned with its numerical direction facing upwards, the vector direction should be set to 0, 0, 1. Click Edit tool and change the support vector to 0, 0, 1, then click OK. Click Measure, select Manual Point Location tool, and click OK. Move the probe to a safe position, click OK, and perform the calibration for the A0B0 angle. Next, adjust the standard ball support rod to point in the positive Y direction. Click Measure, select the T1A0B0 angle, then select all A90B0 angles, hold the Ctrl key, and sequentially select them. Modify the measurement parameters accordingly. Note that the vector direction of the standard ball should be changed to 0, 10, as it is pointing in the positive y direction. Click OK, then click Measure. Similarly, select Manual Point Location tool, click OK, and click OK to perform the calibration for the A90B0 angle. Next, adjust the standard ball support rod to point in the negative y direction. Click Measure, first select the T1A0B0 angle, then select all A90B0 angles. Here, the vector direction of the standard ball needs to be changed to 0 to 10, as it is now pointing in the negative y direction. Click OK, then click Measure. Select Manual Point Location tool, click OK, and click OK to perform the calibration for the A90B0 angle. Once calibration is complete, the asterisks in front of the probe list angles will disappear, confirming that the calibration was successful. If the results are unsatisfactory, recheck and recalibrate as necessary. Click OK to complete the calibration of star probes. In this lesson, we have learned about the detection analysis of rotors and calibration of star probes, covering inspection analysis of parts, clamp workpiece, and calibration of star probes. Through analyzing the parts drawing, we learned how to determine measurement dimensions and establish a coordinate system based on reference points. For part clamping, we used a V-frame or V-block to ensure stability. In the section of calibration of star probes, we learned about configuration, installation, and calibration procedures of probes. Through hands-on practice, we deepened our understanding and ensured the probe's accuracy met measurement requirements. Finally, please reflect on this lesson and complete the following exercises to consolidate the knowledge you learned today and deepen your understanding. That concludes today's lesson. See you next time.